Hello dear students, this is our fifth chapter in 11th grade. It is energy and chemical reactions. Okay, first of all, let's start with defining system and the surrounding. Now, thermodynamic examines physical and chemical changes always in a system. For example, if there's any chemical reaction or any physical change, this is going to be our system. Now, system, surrounding, and universe can be shown as, for example, you have a closed container with a piston here. This is the ideal piston. Now remember, the ideal piston means it has no friction and its mass is not encountered. In fact, this is a piston not existing. And you have an X gas in it. So this is going to be our system. We're going to examine the behavior of the X gas particles, molecules, whatever it is. So what is all around it here? This is going to be our surrounding, and the sum of this system and the surrounding will give you the universe. So these terms are really important for us: system, universe, and surrounding. So universe is the combination of system and the surrounding, and system is the part of universe where the examinations are made on, like our reactions, and surrounding is everything outside that system. So here is the classification of the systems. We classify systems according to their substance and energy exchange, temperature, pressure, and according to volume. Now these systems are, first one, open system. Like what? Like a glass of tea. It can exchange matter and energy with the surrounding. The second one is closed system. In this case, you have some amount of tea in a closed glass, let's say. It can only exchange heat but not the matter. 3. Isolated systems. Now you can think one as a thermos. Now remember, thermos can just keep tea hot but not forever. So for isolated systems, we say that there is no matter exchange and energy exchange is really negligible. The fourth one is isochoric systems. Isochoric systems is like pressure cookers. It can exchange heat and matter. The fifth one is isobaric systems. Now, all the reactions that we carry out in laboratory are done under isobaric conditions, because we say that we have some standard conditions like 25 Celsius and 1 atm. So this means that they are carried out under constant pressure. The sixth one is isothermal systems, like human body. Remember, you sweat when you just get real hot, or you just get cold when the weather is cold. So this means that your body trying to keep your temperature at 36.5 Celsius, something like that. So you just exchange heat and matter in order to just keep that temperature constant. Okay, let's define internal energy. Now, all the kinetic energies coming from the particles in a substance, spin, translation, vibration, and all the other potential energies coming from the attraction between the proton and electron, proton and neutron, or vice versa. These all make up the potential energies. So when you all just sum them up, you're going to just find the internal energy for a substance. Now remember, you cannot just measure an internal energy. There is no some kind of device measuring that energy, but you can only measure the internal energy change. And here it is. There's a note here: for ideal gases, electrostatic energy is accepted to be as 0, because remember, if a gas is ideal, this means that it has no attraction between its particles. So this means that there is no attraction between the molecules and there is no electrostatic energy. Okay, now comes between the difference between heat and work. Now heat is the energy transferred because of the temperature change, and work is a type of energy because it transferred other than temperature change. So for example, you have two figures here. This is the first one, this is the second one. Let's say that this is volume initial, and let's say that then you have a volume final. Now when you define work in physics, you say that you're going to just multiply the amount of distance by the net force with the net force. So in chemistry, work is explained as minus pressure times delta volume. So when you look at this figure, W is equal to minus pressure times volume final minus volume initial. So when you have really the numbers and when you calculate that work, you're going to find that work is going to be smaller than 0. So what is the meaning of this 0? This 0 means system does work against atmospheric pressure. So this means that it is going to spend some energy in order to expand that gas and lift the piston up. So that's why we show that amount of energy with a minus sign. And let's start with the law of thermodynamics. Now you have the zeroth law of thermodynamics. Zeroth law of thermodynamics is used for identifying temperature and also developing thermometers. So here it is. There's a thermodynamic equilibrium here. If the first object's temperature is equal to second one, and if the second one is equal to the third one, this means that the first one and the third one is at thermodynamic equilibrium. So this is the idea of zeroth law. Now, what says the first law? Energy cannot be created nor destroyed. So if you are talking about a delta U here, delta U is equal to amount of heat given or taken plus amount of work here. Now please, when you're solving the questions, be careful with their signs. Signs of Q and W differs on different occasions. They can be positive and negative. system is delta S reaction. This is going to be equal total entropy of products minus total entropy of reactants. So when this entropy of system changes, entropy of the surrounding is also changed. So this is minus delta H reaction over the temperature. And finally we have delta S universe. Delta S universe is equal to delta S system plus delta S surrounding. Now, when you calculate all of these and find the entropy change in universe, you're going to just say that is delta S universe is higher than 0. Now you have a spontaneous change. Now delta S universe is smaller than 0. It's going to be a non-spontaneous change. If delta S universe is equal to 0, in this case you have a reaction or a physical change at equilibrium. This is going to be our next chapter. So you can also decide the spontaneity of a reaction by using the Gibbs free energy. So Gibbs free energy is a thermodynamic function that makes it easier for us to decide whether a reaction is spontaneous or not. Now, for example, you have the delta S surrounding. Remember the formula? It was minus delta H over T here. Now, delta S total was delta S system plus delta S surrounding. So when you write this formula instead of that delta S surrounding here, what's going to be like delta S system minus delta H times temperature. So this is delta S total. Just will you please multiply all this equalization by minus temperature. It's going to be like minus T times delta S total is equal to minus T delta S system plus delta H. So this is known as delta G here. So delta H minus T times delta S will be the formula. Just discuss now and remember when delta S, this one, when this one was higher than 0, then you have a spontaneous reaction. But in this case, if there's a minus here, then when delta G is smaller than 0, it's going to be spontaneous. When delta G is higher than 0, it's going to be non-spontaneous. If delta G is equal to 0, it is going to be again at equilibrium. So if we summarize, what do we have? We have delta H, okay? We have delta S, and we have delta G. Now delta H can be calculated from total heat of formation of products minus total heat of formation of reactants. What else? You have Hess law, or what else? You have bond energies. Total bond energy is broken minus total bond energy is formed. And now what about delta S? You have 3 different types of delta S's. You have delta S system, meaning delta S reaction. Total delta S products minus total entropy of reactants. Now you have delta S surrounding. This is minus delta H over T. Now that you have the delta S universe, this is sum of delta S system plus delta S surrounding. Now comes delta G. There are 3 ways of calculation delta G. The first one, this is minus T times delta S total, or this is equal to delta H minus T times delta S. And finally, like the delta H and delta S, you have this is equal to total Gibbs free energies of products minus total Gibbs free energies of reactants.